My name is Eric Normand, and I'm writing a book called A Theory of Functional Programming. And I want to talk about a certain topic from that book, and I'm going to use the transcript of this video to help me write the book. So everything here might make it into the book. At least the topic's going to. Who knows what's going to happen with the editing. All right. So what I want to talk about is this issue of what is an action and what is a calculation in terms of timeliness. Because we know that deep down in the computer, everything is an action. Every operation depends on what is at particular locations in memory at the time that the operation is run. So even like addition, an addition, in the mathematical sense is a calculation. It's timeless. But when you run the add instruction, it reads two locations in memory, which are mutable, and it writes to a location in memory, which is also mutable. So it is an action deep down in how the machines work, because our machines are based on the idea of a Turing machine, and so it's all actions all the way down. So how is it that we can claim that we actually have calculations? And it's just through discipline. The disciplines of our compiler, or even just as programmers, we set it up so that those registers don't have anything important in them, so we can overwrite them, and we're going to pull the value right out of the register and put it on the stack or store it in a variable right away. So we've got these disciplines that allow us to do the operations in a way that doesn't depend on when it's run, right? And like I said, the disciplines are either enforced by the programmer or by the compiler, and both of them are fine. The compiler makes it a lot easier on the programmer and avoids a lot more mistakes. So in a sense, it's all an illusion, the whole idea of timelessness of calculations. But it's a very valuable illusion, and we can make it pretty safe, pretty reliable. Now, there's another issue, though, which is that you have language like Haskell, as a really good example of a functional language. It has a very hard line that it draws between calculation and action. The calculations are function types, right? So all of the functions are pure, and so they're calculations, and I/O is reserved for actions. So the thing is, that's a great line. That is where it should be drawn between, as a language making this choice for the programmer. That is the right place to put it. But there are some actions. Well, let me put it this way. What if I'm writing and reading to a file? That's definitely an action. You can't really control the file system. It's shared by all of the programs that are running on the computer at the same time. They can read and write to it at the same time as I do. And so it's definitely a timeful thing, right? It's bound up in the time, because I could write before they write, or I could write after they write. It really changes things. But what if I were to add a lot of discipline to my program to lessen the chances almost to zero that someone else would be writing and reading at the same time as me. So I would generate a new temporary file with a random name so that no one could guess it, and I read and write to it very quickly and then immediately delete it. So basically there's near zero chance that at any moment another program could guess the file and read from it and write to it and mess up my code. In the same way that the operating system will protect the memory, saying like, you can't read that memory from this other program, you can't write to the memory of the other program, right? So you're enforcing a similar discipline. So would that still be considered an action? Does it matter if it's a near zero probability that someone can mess with my code, and I do it in such a way that it's a pure calculation? I just needed a temporary file to hold some values for me. You can argue, and I think it's the right way to argue. You can argue that that is not an action, right? You're using discipline to ensure that that it doesn't depend on when it is run or how many times it is run. And so we can move that into a calculation, right? And in fact, Haskell gives you a way to take something that is typically an I/O, meaning disk reading and writing, disk I/O, and any kind of I/O, but just in this example, disk I/O is an I/O. And so they give you a thing called perform unsafe I/O. And what that does is it takes an I/O and turns it into a calculation. So that's great. Haskell knows that this is a thing that you're gonna run into, where sure it's I/O in the general sense, but in this particular case, I want the compiler to trust me that I know what I'm doing, and it should be a calculation. That's great. Similarly, if you have a calculation, it's a pure function. It's like a statistical calculation, but it uses big data. And so it takes a long time to run. It's a very complicated, convoluted algorithm, but it's pure. Like this, you run it twice, you get the same answer. But the issue is it takes 24 hours to run. Okay, so in general, this would be considered a calculation because it's pure. But when you start running it, you're gonna wish that you had started 24 hours ago, that yesterday, and you're not gonna know the answer until tomorrow. So it does matter when you run it. You know, all calculations take some time, but usually it's so little time that we don't care. Right? We don't, 10 milliseconds on the human time scale, we don't care. 100 milliseconds, we don't really care. A minute, maybe we start to care, but 24 hours, we definitely care. That's starting to get into like, is this going to be done by the end of the week kind of territory. So, what do? Well, we should call that an action. Right? It does matter when you run that. So, what I'm trying to get at is this principle that this is an illusion that we are building, and in many cases we can get away with it because everything takes time. Everything has a side effect. Excuse me. Everything has a side effect of using memory. So it's putting memory pressure on the garbage collector. It's using one of the CPUs while it's running. So that's affecting the scheduler and what other things can run at the same time, how long other things take to run. So it all does have an effect. It's generating heat, it's using electricity, all those things. But we ignore those. Just like in a physics problem at school, we would ignore friction. Even though we know it's there, we know that there must be friction. We just don't count it. We know there's air resistance, we just don't count it. Because the answer you get is good enough without it, even if you ignore it. And so we do the same. We say this calculation is timeless enough. And so we just don't care about the time it takes. Okay, so some languages, like I've said, give you a little bit more support in the discipline. So for instance, Haskell gives you a lot of support because its functions are all pure by themselves. And Clojure gives you a lot of support because it has immutable data structures. But I believe that functional programming is something you can do if you know what you're doing. It is possible to do it with purely programmer discipline and not explicit support from the language. And this is why, because it's all a choice anyway. It's all a system that's built up by the compiler and the programmer anyway. All right, so this has been me talking about the illusion that we're creating when we're doing functional programming, an illusion of timelessness, an illusion of timelessness of data as well. So a lot of languages don't have immutable data structures. Everything is mutable. So even if they have what's popular now is having a variable that is unchangeable after it is set. So in JavaScript you have const, right? So even if you use a const, if you assign an array or an object to that const, you can still mutate the array or the object. So it's not really immutable. It's only like one level of immutability. What you want is to guarantee that when you generate data, it is an actual bit of data. It is a value. It is not a place that can change. It's not a place for storing stuff. It is a record, meaning record means something that you keep forever, right? That you've recorded and it's stored forever. I don't know if I've talked about that enough. The data is a fact, a recorded fact about an event that happened. Okay, so this is the definition of data we talked about before. By record, it means that we want to keep it. You record something to keep it around later. We've lost that idea of record generally in computing, in software, mostly because we had a very limited amount of storage space. Hard drives were expensive. RAM is certainly expensive. And now we're starting to remember that in any other information system outside of the computer, say an accounting system or a medical record system, when you say I have a record, it means it's permanent, that you want to keep that record around forever. You don't want to change it. So, there's typical threat at school, at least here in America, that any absences will be marked on your permanent record, and that's exactly what we want. We want things to be stored forever. It's permanent. Now, of course, that permanence of storage doesn't really count for stuff in RAM, because if you turn off the computer, boom, you've lost it. But we do want it as a transient place to store something before it gets recorded. Putting a record immutably in memory so that we don't have to worry about it being overwritten. That is very useful. So I think as a discipline, functional programming moves toward this immutable data structure approach, because it allows you to reason very locally. You don't have to worry about who else has a pointer to this data structure if it's immutable. Right? You can just rely on it never changing. Whereas if you have mutable data structures, you have to have a very strong trust, a very strong contract with the clients that are using you about ownership and what you're allowed to mutate, because the language will allow mutation. So there's a lot more non-local reasoning that you have to do. Right? You have to say, look, I'm going to give you this value, but it's not yours. I'm just letting you read it. Do not write on it. I'm letting you borrow it, but return it in the same way that you found it. Right? Whereas in an immutable thing, that's enforced by the runtime. And often what we'll do is we will, to help enforce the safety, we will use a discipline called copy on write. Or something even stricter, which is copy on share. So every time someone asks for a value that is mutable in the language, say an object in JavaScript or an array in JavaScript, every time someone asks for it, you make a copy and pass them the copy. So they get a fresh one. And you don't have to trust them anymore. You can write all over this if you really want to. It's not going to affect me. The problem is that's very wasteful in terms of memory, and it can easily get out of hand. For instance, copying an array is a linear operation. And so if you don't know that it's copying, right, because this is part of the contract, you have to tell them, hey, this is now, reading this value is now a linear operation. Now it can become accidentally quadratic, because what if they ask for the value not knowing that it is linear? What if they assume it's, let's say they just assume it's constant time? It becomes accidentally quadratic because they're asking for it for each element. See? This is why we it complicates things to have mutable things. Because if you want to enforce it through discipline, you just have to have all these checks, or you have to have a trust, you have to have a contract that's better understood. Whereas immutable is a very simple contract. I'm going to give you something, you just can't write to it. You can try, it's not going to work. It's easy. It's very easy to reason about. All right. I think I've talked enough about this. Thank you so much for listening. Tell the robots what you like so they know how to share and recommend to other people. They don't have emotions. They can't tell what's good. Let them know. Let them know what you like. Hit those buttons. Mash them. Subscribe. And sorry about the audio for some previous videos. I really think it's my headphones. Not these. I switched back to these. These don't work so well, but I think the microphone is fine. So sorry about the audio. I bought a new pair. They're in the mail. We'll see how they work. Awesome. See you later. Bye.